Alright guys, so we are going to go over the day 2 of TypeScript, the OOP day. I'll probably take this a little slower than I took day 1. First I just want to preface why we're focusing on OOP as much as we are. I know it's been kind of hard to teach OOP, but I think it's a pretty important concept. It's going to really help them with job placements if they can understand some of the basic concepts, which we have never covered. So we really do want to make sure everybody understands some of the core concepts of OOP, like inheritance, interfaces, overriding, polymorphism, the abstract classes, and the idea of programming an interface or programming to supertype. So that's kind of really our focus here. There is a whole section on generics here. I would say this is more for information. I don't think, at least for our use cases, are going to really need to use generics too often, but they are going to see them, and they should be aware of them, especially some of the type stuff here at the bottom here, the utility types, built-in utility types, because we will be using those in day 3 a little bit. We don't really go over them. We talk about what they are, but we will be using a couple of these that are very similar to our. We'll be using something like this, which we make our own version of here, which we can just use from that website. All right. There is homework to here, and it's basically exactly our step that we're going to get to when we go through the OOP design process. All right, and this is a long notebook. There's only 2 exercises in here for the students to do during class. Because it's so long, I didn't really want to add too many exercises to slow the class down. But it would be cool if you think you have more time to add some more. And of course, this does use the TS Lab kernel. Once again, you can always just double check, make sure this is TypeScript, and you can always change it using change kernel if for some reason it opened with the wrong kernel. All right, we do have our beautiful index. So object-oriented programming, we're just going to talk about the basics of what it is and how it's a model of a real-life entity. So here we're going to make a car because we've made cars before. I thought it was an easy way to intro. So you can define the types of properties up here when you are trying to make your class. So generally, right, we would just have something here and say this that make dot equals this dot make equals make, and that would be doing our work for us. But we can actually, to define our types of properties, we're going to define them up here. So we're going to say make is a string, model is a string, and year is a number. And then we have to name our parameters in our constructor as well. And you can see here we are making sure we have our parameters and our return type denoted for our functions or our methods. So this is just a basic car, nothing crazy going on here. Just kind of explaining the basics of how OOP works. Again, just kind of reminding everybody what a class is and how we access stuff. So here we go, we're driving, and it says we drove 15 miles. Perfect. So we also have different ways to declare our properties. So here we're going to actually make a property read only because IDs, right, shouldn't ever be changed. So we're going to make our ID property read only. So now you'll see when we make our new car, we can assign an ID to start, which is fine. Obviously, we could set this up with something like UUID or just some other way to create a ID for us naturally. But we're just going to say we're going to assign it here. But what you'll notice now is when we try to reassign our ID, here we take our second DeLorean, we change this ID, and we say ID can not be assigned because it's a read-only property. So we've now prevented anyone from changing our car ID, making it a read-only property. Easy enough. So we also have optional properties. So in case we say that, hey, you don't always have to have something, we can give it, make it optional. And in this case, we're going to make a optional nickname for our cars because, some cars like Herbie or Kit from Knight Rider, they have cool names. But, my Mazda sitting out front, it's just a car. It doesn't have a fancy nickname. So it's optional. So we're just bringing in all the stuff that wasn't optional, and we set them all here. And we use this question mark. This is what's making it optional. We say question mark and then colon, and that now makes it optional. What you're going to see here is that we're cool. We don't have to, give it a nickname. and we can assign a nickname to it, though, if we want to. Note that this wouldn't have worked. We can't just dynamically add keys with TypeScript, so I couldn't have done this and just said that works, and like we could with vanilla JavaScript. We do have to have it up here, and it does need to be optional if we want it to be optional. Other than that, it would be required, and we wouldn't be able to initialize this class without it. All right, so that's optional. That's read-only, and that's just kind of your basic way to define attributes. What we're going to find here soon is there's easier ways to write our attributes, but there's something more important we need to talk about, and that's called access control keywords. All right, so this is a really important subject. If you learn Java, you have to know what these are. If you learn C++, you're going to need to know what these are. When you're dealing with object-oriented programming languages, these are very important. So Java actually has an extra one that we aren't going to see here, but this is very similar. Everything in TypeScript is very similar to Java. So once you learn TypeScript, OOP, moving into Java is going to be a lot easier, which is going to be really nice to be able to have this for the students to start learning. So when they do get out of here and they want to pick up Java, they're not going to be completely lost. So what do these access modifiers mean? So these go on your variables, just like we had our read-only and our optional type things. We also can make everything has an option of being public, protected, and private. By default, everything is public. All right, so what does public mean? Public means it's accessible anywhere. So I could use it out. I could edit this property outside of my class. I could edit in my class. I could edit it in children classes of my class. But protected is a little bit different. So public pretty much says you can do everything that you expect you can do with it. These other two limit it a lot more. So protected means you can only use that property from within the class. So if I'm using something inside of here, inside of my actual class declaration, one of my functions or methods, I could use that property. Or in one of the descendants of cars. So if we made a electric car that was a type of car, I could then access that protected variable inside of that class. But I could not do something like this and access it from outside of the class. So this is accessing something outside of a class. This is accessing, if I use this dot something in here, this would be accessing something inside of the class, which we're not doing. And then accessing something that's private. So then we have private ones. These are even a little bit more different. These can only be used from within the class that declared it. So that means even if I extend from that class, I cannot touch the private variable. So these access control keywords are really key to the idea of encapsulation. So this is a keyword. We definitely want to make sure they know this term. This is an important term. So it's basically the idea of hiding your data and to prevent properties from being modified or used by other people or programs that shouldn't be using them. And in that process, you can also control the modification of these processes as using your getters and your setters, because you can say, hey, if you want to change this property, that's fine. I will provide you with a public setter, which will allow you to now change the property, but I'm going to have control over how you change that property. I'm going to be able to I'll have the final say, right? So I'll be able to make my own modifications with my getters. So that's what a private variable, that's the idea of encapsulation. So, which we'll see here, we're going to kind of do this in an example here. So here we have our types defined. And now we've made a whole bunch of them public. And then we made the ID private. Now, why we made the ID private, there's not a really good explanation for that in this use case. Mainly just so we can do this as an example. Generally, your private methods and variables are things that are helping your class work that maybe aren't important to the person using your class, but you need them to make your stuff work. You'll see an example of that when we go through the project. Make that a little more clear. So here we have public, 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 public. So everything else is public. So what you're going to see here is we can give our car a nickname if we want to. Well, first we'll see. We've made a car. We've given ID 1 DeLorean DMC 12 in 1981. All right. So if we go print info there, we do see the car ID 1 is a 1981 DMC that has no cool name. That's fine. And if we would to, have a nickname, it would be a little bit different, right? Now we have that is called the DeLorean. So this is just showing that this is still optional. Nothing too crazy going on there. But now let's see what the effect of that private variable is. So the fact that this is now private means when I say DeLorean.id, right, I can't actually see it because it's not accessible outside of the class. And now we're accessing from outside of the class using the instance. So literally when we say outside the class, we mean this class structure inside the braces of the word class. All right, but I could still come in here if I really wanted to, and I could say, you know, dot make or something, right? And we can do dot make, and we could run this, and we would see that works, right? Because that's a public property, so we have public access to it. But once again, the ID is just a private property. Cool. So it's private. Now we're going to make this a little more simple now. So a couple things here. We can actually, instead of putting all this stuff here at the top, we can actually declare it all inside of our constructor input, and it will essentially do this for us, and we can skip this part. Makes life a lot easier. So first I'll talk about that. So if we look here, instead of putting all the types of properties up here, we still put the nickname in here because it's optional. So if we have it in our constructor, it's going to be required, or we're going to have to make this like string or undefined. And, you know, I'll just put it up here to make this a little more easy to deal with. But here we have all the ones that are required, and I can declare them private, read-only, and put in their data type all within the constructor's parameter list. So that's pretty cool. So instead of having to do all this work we did up here and then having to do all this inside of here, we can literally just write this here in the constructor. You know, my constructor is actually empty because I don't need to do anything necessarily to build this thing. So we have it empty, and we're just assigning our properties. All right, easy enough. Now the other things we're going to mention here is what the convention I use in this notebook is not necessarily a great convention. It's a older convention. Many will argue that this is not applicable anymore. This convention is actually used in the TypeScript website, but if you read the Google and the Apple style guides, they say this is a terrible convention. And what I'm going to be using is underscores for our private variables. And then when we use a protected variable, I'm going to end it with a $sign. And most of that is just to make it more obvious why we're trying to teach this, that one is private and one is protected. And the rule of thumb nowadays is generally to either use a variable name that just makes more sense to you somehow, which I just always think is crazy. Because if you're going to have a getter for it that's public, I mean, it's basically going to be the same name. I like the underscore way. But generally they say don't do that anymore. Make the name, you know, some cool name, or use whatever convention your company has, which is generally the case. You're going to have some convention you're going to use. And I've seen a lot of people say that this is the convention they still use. So, you know, it is what it is. And it's just what I'm going to be doing today. All right. So that's why we do see here that I called this underscore ID because it's private. So I wanted to note it as private. All right. So the whole point here is that this all works just like it did before, but we have moved now this like this instead. So awesome. So what if we actually want to use these things, these private variables, we're going to need to make getters and setters for them. And we really should make getters and setters for everything. So actually, generally speaking, most of your variables are going to be private, and then everything is going to be, your methods that are private are generally the ones that you're going to be using for yourself. But your variables, your attributes, your properties are usually going to be private for your class. And you'll use public getters and setters because getters and setters also can have access modifiers. So I'm not writing this in here, but all these are going to be public. And I'm not going to really talk about that too much in this notebook, but we could make these public, protected, or private as well, which would have its own, issues, depending on what you're trying to do. So if we want to actually be able to keep our encapsulation, we want to make most of our stuff private. And use getters and setters for it. So in this example, we are going to make the car's make and model, make it so it cannot be changed once we make them. But the nickname can be changed. So we're going to make the nickname public, and we'll make the model and the make private. And we're going to make our getters. So getters are pretty simple. We just say get, and then we'll say make, and we'll execute, and we'll say this is going to give us a type of string. And we're going to return this underscore make because that's our private variable. So now if we just say car.make, we'll actually get this underscore make. Awesome. So once again, this is just talking about setters or getters. Now what I decided to say, maybe we wanted to have a fancier version of our get statement. This is kind of why we have these things, is because maybe we don't want them to directly access information. So what we're going to say here is, if there is this dot underscore model, so we've already created a model, then we'll return this dot model. Otherwise, we'll return no model data. And we didn't make model optional, so that would mean if this string is empty. So here we're going to make a new Knight Rider, new car. He's a Pontiac, and I forgot to put his model in, so it's blank, and we have Kit. And you see we printed it out here, and I can still see his nickname. So we did not make nickname optional this time. So you do see nickname here. Public properties can be changed from the outside of the class. So here I can change the nickname for Kit to Kit 2000, right? Because it's public. So you see that we have officially made that change. But private properties cannot. So here I'm going to use underscore make, and I can't even view it, let alone reassign it, right? So we know that's a problem. But if I use dot make, which was our getter function, we tend to use, that same syntax here. So now I can use dot make, and we will see that I can see it's a Pontiac, and I could actually I can't use that to set it because we don't have it in a setter yet, but this is how I would use it for a setter as well. I would assign this to something else. But right now we just did getter, so I can only get it. I couldn't assign it. So even if I came here and said, this is equal to potato, and then I came over here and tried to look at this model, no, I didn't run any of these cells, sorry. All right, hold on. There we go. So it says I cannot assign it to make because it's a read-only property. And you see that I don't get anything there. And you do see KnightRider.model is giving us no model data. All right, I'll just run that back the way it was. Perfect. So that is our getter. So that's all the getter does. This is, once again, is part of our encapsulation. We want to make sure all of our variables can only be changed in ways that we have pre-approved. So basically, we have to make them go through the getter to return it, because maybe we want to do something different and not return them exactly what we've stored. Maybe we have some other thing we need to do before we give it back to them. The same kind of deal with setters. So the next section here is setters. So this is how we can actually change our things. So we've made a getter now for make, model, and then I have something called make model, which will return both the make and the model. So now I can actually make up attributes that aren't part of my actual class properties here, right? And we'll be able to use this, and it will return us the string of whatever the make and model is. And so that's pretty cool. So we've made getters for our 2 private variables and 1 for a variable that didn't even exist. And now we've made some setters. So now I'm going to be able to set make. So that's going to take in our new make, and it's going to be a string, and we'll just say this underscore make is equal to the new make, because I can access this from inside the class, even though it's a private variable, because that's what a private variable means. And we're going to run, we can now do this, right? So we have now made our setter. So we have our setter for model, same kind of idea. We're bringing in a string. We'll be able to set it to whatever this is. And what we're going to say here now is we're going to have some rules. So I said Pintos are just terrible cars, and they should never be allowed to exist. So if there is a new model, and that new model is equal to a Pinto, or is not equal to a Pinto, sorry, I will set this equal to new model. Otherwise, I'm going to say the model is wrecked. So if you put in Pinto, we're going to get back wrecked. This is just kind of showing that, the reason why we have setters is that maybe we don't want to automatically just believe whatever the programmer's doing. Maybe we need to check it or change it or manipulate this input and to make it fit with what we want our variable to really be. All right, so here I've made my new car. It's a Pontiac. It's Kit. And we see the output. All right, nothing surprising going on there. And now the setters allow us to actually do things. So, whoops, let me run this again, and then I can run this again. And we can see what has happened here is, one, make model is showing me my make and my model. And here I set the make from BMW from Pontiac, so we were able to change that now. And then I try to change the model to Pinto, and you note we don't get Pinto, we actually get rect. And that's because we're using our setter, which prevented that information. Awesome. So that is your setters and your getters and access modifiers. So pretty cool. We will talk about protected once we get into the inheritance section, but we will get there later. So what we're also going to talk about is something called index signatures. So it's going to allow us to dynamically change the properties of our class. So in regular JS, as we said earlier, I could do something like this where I just said, hey, KnightRider.year is equal to 1982, even though we don't have a year attribute on this class. And I can just set it here anyway with regular JavaScript. Oh my goodness, where'd I go? Right here. But as you see now, I can't do that. I can't just make up a key and set a value to it. So if we want to be able to do that, we have to do something like this. So this is a index signature. So what we're going to say is we're going to have Pokemon ratings, and they're going to be, the property name is going to be the name of a Pokemon, and then its value is going to be some number. So we use these brackets to define the key. So we can give the key whatever we want here, and then set it as a type of something. And then what the value of it's going to be is a number. So over here is the return value of this attribute. And this is just saying that this is a string attribute. So this will be a string that we give it, not a number or a list or some other type of data type that we're trying to put here. So here I'll say let my ratings equal new Pokemon ratings. And then I'll say ratings, and I'll put in, notice I can't use dot notation here, right? Because we are trying to put in a string, so it just wouldn't make any sense. So I'll put in Arceus, and I'm going to set his rating to 1 because he's the best Pokemon there is. Let me run these cells in order here. There we go. And we can see that we have now added a key to our ratings of Arceus, and it has an integer value of 1. But if I try to put in a string for that value, it's going to say string is not assignable to the type number, because we did say in our signature here that this needs to be a number for the value, not a string. And then over here, I can't use a list, right? Because we said this needed to be a string on this side. So this has to be a string. And note, if I try to make it something that's not a string, like a list of strings or an array of strings, we're going to have an error. So that is index signatures. Perfect. Now we're going to talk about static keyword. I only touch on this. I do think it's important that everybody understands what the word static means. The static keyword denotes that a property maintains its value across all instances. All right, we do have static properties and methods in Python as well. It also must be used without the instance, and that's not always the case depending on the language, but usually you can't use it with the instance. So to access a static property, we will call it by its class name. So we'll say class name dot static property, and we can get that. So what we're going to do here is we're going to make a class called counter, and we're going to make a public static count, and we're going to call it a number. So this is going to be, obviously we're going to initialize it to 0. We could have actually left this off, right? Because TypeScript would say, hey, you started with a number, it's going to be a number, but we decided to be a little explicit here. We're going to have our little method here to increase our count. Note that I'm referring to the count using my class. So I say counter, which is my class, dot count to get my attribute. And I can do this because it's public. Obviously, if this wasn't public, I would have to make getters and setters that are static for it. And we'll say dot count, and we will add 1 to the count. So every time we run increase count, we're going to increase our count by 1. And then this will just log out what the counter is. And note we're still using counter.count, not this dot count or something else. This is a static method here because this method needs to be static. Well, it doesn't have to be static, I guess. But we're going to make it static because there's no reason for it to belong to an instance because it doesn't know anything about an instance. Note we're not using this. We don't know anything about the instance. All we care about is showing back our static count. And what we're going to see here is pretty cool, is that no matter how many different counters we make, anytime we use increase count on our instance, we will be increasing the same counter. So they share the same counter across all instances of our class. That's what the static means. So here we're going to start by console logging our count, and we're going to see we have 0. Now I'm going to make a new counter. Oh my goodness. Click all these buttons here correctly. All right, so we make a new counter, and now we're going to say counter1.count, and we can't access count, right? Because that's not how we access static properties in JavaScript. So we're going to come down here. All members of the counter class share the same count property. So we're going to really see what's going on here. So I'm going to say counter1.increaseCount, and then I'm going to say counter.count. We're going to see what that is. Then I'm going to make a new counter, and I'm going to increase the count twice on that one, and we're going to see how the count has changed. And what you see is that once we increase it once, our count is now 1, and we make a different instance of counter, and it's going to increment that 1 to 2 when we do the +1 twice. So they are sharing the same property across all instances of the class, and that's what it means to be static. Awesome. So if we want to use our static method, I can't say counter.showCount because that is a static member of counter, and we can't access it that way. I have to use counter.showCount, and you'll see that the count is 3. All right, pretty simple there, but that's the idea of static. I'm going to try to drop away from talking about static here. We will keep it in here, this one inheritance example for the first example, and then we'll drop it. All right. So what we're going to do now, and this is kind of the theme of the rest of this lecture, rest of the OOP part of this lecture, is we're going to be building a duck class. And we're going to have children classes to represent different types of ducks. We're also going to use the protected modifier for the first time, just so we can, since we're using inheritance, we can actually talk about it now. Remember, protected means it's available to the class that declared it and any of the children classes, but not from outside of the class. We don't use protected as much. Lots of times, generally, it's better practice to use private. Almost always is better practice to use private. So protected, it's used, but not as much, because generally, as you expand your project, having things protected can cause more issues, because it means you can override all the getters, and if those getters and setters are actually important, you've now maybe screwed stuff up. Otherwise, you could just set them all to private, and then in your child class, you can access the getter from the parent class, and you can make your own getter for that property doing it that way. All right. Another thing to note, in Python, they have what's called multiple inheritance. This is not possible in TypeScript or Java, or I don't even think it's possible in C++. It's just not really a very good way to do things, to be quite honest. So you can only extend from one class in JS and TypeScript, and that's because of the diamond problem. So that's when two classes have the same two classes have the same base class, and we don't really want that to happen. All right. So how we can actually get around this problem is by using interfaces. And we can actually allow them to implement many interfaces. So interfaces, you can have a whole bunch of them. And that's really the key when you're talking about OOP, is you're wanting to make things, you're really trying to design to an interface that you can now use with everything. So you can you have a defined set of rules that your classes can talk to each other with that are defined by your interface. So let's get into this real quick. We got our class of duck. All right, pretty simple here. Public static class name, and it's a string, and we are going to set it equal to duck. So we just made a class name on our duck, just a public static property. So we would do duck.class name, right? All right, we got our constructor. All we did here was say we have a protected variable called age, and that's the only thing we put in here is one protected variable called age. And I made a get age to return the age. I didn't make any setters for it. And then we have a ability to quack and an ability to swim, and we made these public methods so we can have our generic quack sound, and we can have our paddles with 2 little feet here. Then we're going to console log duck.classname. You see we do get duck, just to prove that that is there, and it is static. And then we're going to make Daffy duck. So Daffy is equal to a new duck, and he's 39 years old. And we're going to make Daffy quack, swim, and get his age, and we can do all that just fine. Note, I couldn't get age $sign if I tried to do that, because we're outside of the class. I would get this error that's saying that age is protected, meaning I can't access it from outside the class, but I can't access age because that's our getter that is public. All right, so that is our parent class of duck. So let's make a mallard duck to extend from it. So we're going to make a mallard duck first. It extends from duck. So this is how we do inheritance in JavaScript. We say extends, same thing you do in Java. Once again, TypeScript and Java OOP is very, very similar. So we got class mallard duck extends from duck. So in Python, remember, we would have put duck in parentheses after the word mallard duck here, but we use extends. Now we're going to say our public static class name is mallard duck. So here we are overriding the property class name in our child class. So this is called overriding, right? And here we're going to have our constructor. It's going to take in a color and an age this time. And we're going to run our super age so we can run our super constructor, which took in the age variable to make our duck class, right? So this is very similar to Python. Note in JavaScript we use super like this, not def underscore init, blah, 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 which we talked about that already in the JavaScript week. So there we go. We have made our mallard class. So what we're going to do is here make a new mallard. So let mallard equal new mallard. We're going to make him brown, and he is 2 years old. And we're going to console log mallard class name. You see that we do get it is a mallard duck, but the duck.class name is still duck because those are static, and we have overridden the mallard duck version, but duck never lost his version there, right? If I go look at mallard.age, I will see that his age is 2, and we can see it because age is public. Note I didn't put a access modifier here, so that means this is public. Obviously, it's better practice to put that public there. Mallard, quack, and swim. What you see here is I didn't redefine or override any of those methods in the child class, so we are getting the parents class's implementation. So we're going to get generic quack sound and paddles with 2 feet. And then if I do mallard.color, of course, we'll get the color of our mallard, which is brown. Now, if I go back and I try to use Daffy's color and figure out what color Daffy is, we all know Daffy was black, but, you know, Plucky was green. But, you know, I can't do that because ducks don't have a color. Because remember, Daffy is a plain duck, and plain ducks don't have color. All right, so now let's talk about how private variables are not accessible in child classes. So here, real quick, I made a class called TV with a private serial number string. And I made a class called Roku, which is going to extend the TV. It'll be a fancier TV, right? That's a smart TV. And it's going to be able to say show serial. And we're going to say console log this.serial number. And what we're going to see is that when we run this, I can't even get to this point, right? Like, it's not even going to let me try to do this because serial is a private variable, and it's only accessed within the member of the class here. So what you might want to show them, though, is if we change this to protected and we run this again, it does work because when it's protected, it's going to be available in our child class. Yet we still could not come here and say myTV.serial num because serial num is protected and it's only accessible in the class TV and its subclasses. All right. Perfect. Method overrides. So we're going to talk about method overrides. And of course, we've kind of already talked about that a little bit. Really important idea here, knowing what override means. All right, so first we're going to talk about implicit overriding. So what we're going to see here is we have our duck class with quack and swim. And we're going to come down here. Oh, we also have a getter in our public class that returns this.age. Note that age is a protected variable in this case because we're going to be able to have access to this to age $sign in our children classes. All right, so now in our children class of mallard duck, we're going to change it again this time. I guess I don't need to put that here. Sorry. All right. So we're going to say public static class name equals mallard duck. Same kind of deal. We have our constructor. We still use our super constructor, blah, blah, blah. All right, and what we're going to do here is on our getter for age for mallard ducks, we're going to pretend like any mallard duck is 5 years older than it would be if it was any other type of duck. Kind of a silly idea, but just to kind of show this use of getters. So we're going to pretend like mallard ducks are always 5 years older than other ducks. So it's going to be initialized with an age, but we're going to return that age plus 5 when we want to show the age to somebody. So here we're overriding implicitly the age property. So the implicit part comes because these have the same name and the same parameter list. Now we're not going to get into method overloading, which is not a feature of TypeScript, which would allow us to actually have multiple versions of this with different parameters. Another cool thing we could talk about, but we're not going to get into that. So we have age, and then we have quack, and quack is also going to be overriding our quack function here. Once again, this is going to be implicit because it's going to say, hey, this is the same name as you have in your parent class, and whenever you're looking for a method, when you call it from an instance, you're going to look in the lowest level class, your class, and then you're going to look in its parents' class, its grandparents' class, and so on up the chain. So this one will get read first. And it's implicitly implied here. So we make our mallard duck. We see its class name. We can see its age. This is the same example we did before. We can see all this other stuff. But now when we quack and swim, we're going to get a mallard quack. We still get the same swim because we didn't override swim, but we override quack. So now we're getting mallard's quack instead of a generic quack sound. Awesome. So now we're on to explicit overrides. And unfortunately, this TS Lab notebook runs 4.1. And the override keyword to make explicit overrides did not get support until 4.3. But it is considered to be really good practice and be really bad practice not to use it. And we're almost on version 5. If you haven't seen that yet, we're almost at version 5 of TypeScript. It's in beta testing right now as of March 2023. The override keyword is useful to denote this. It also, if you screw up putting the override keyword, you'll get an error saying, hey, look, you're not overriding anything, so you must have made a mistake. So that's pretty nice. So what we did here is I made a stack blitz right here where you can go check it out. And you can see the use of the override word. So this is the exact same example, except now we're making this explicit by using the override word. So the override can come right here. Or if you do something like this, it would come right here. But it would come after like our access modifier. So if it's in this case here, you see it's over here. If we wanted to write public here, it would still be like this, right? Public here. Or if we made this protected or whatever we're trying to do there, override would go to the right of it. So that's really all we're showing here. By the way, if you're using this, if you want to actually see any output, you'd come over here to the console and you'll see all the output in the console. All right, cool. So that is explicit overrides with the override keyword. Much better practice. All right, so now we're going to get into the idea of polymorphism, another big keyword that everybody should know when they graduate this school. All right, polymorphism, of course, means having many forms. And what we learned in TypeScript so far is that you always need to know the data type of your variables. And if you, say, make an array, you have to define what is in that array. So if we were trying to make a array of our ducks, and we wanted to have mallard ducks and red-headed ducks and other types of ducks all in the same array, well, as long as we had a parent class of duck, we could actually make an array of duck types. And then since polymorphism exists, that means any other duck is a duck. So a red-headed duck is a duck, and a mallard duck is a duck. So I could actually put all my red-headed ducks and mallard ducks and regular ducks in an array of ducks, which is really cool. And the other thing that we want to talk about here is that in OOP, we talk about this thing called the open-close principle. And, this has a lot to do with our access modifiers and our polymorphism here. So software entities, classes, modules, functions should be open for extension, but closed for modification. So it means I should be able to extend the class, but I shouldn't be able to break that class when I extend from it, basically, right? I shouldn't be able to modify all the inner workings of my parent class, but I should be able to extend to it and add to it and modify it. Modify the behaviors in my child class, but not the parent class. Polymorphism is a very important way to help achieve this goal. So let's make a new type of duck, the red-headed duck. All right, so now we're going to have two different ducks. Red-headed duck extends from duck, and it's just going to have a different type of quack. It's basically the same thing we had before, and it's going to age a little different. So they age slower. They're going to get -1 on their age. All right, so now if I wanted to make an array of ducks, I could say let duck array be of the parent class duck, because now duck, mallard duck, and red-headed duck are all of type ducks. Otherwise, I'd be really kind of SOL. If I try to make this a mallard duck array, I could only put mallard ducks. If I made a red-headed duck, I could only put red-headed ducks. But I want all my ducks all in one row. And the only way I can do that is by making a duck array. And then I can put any type of duck. And the idea of polymorphism being that this mallard duck is a duck, and so is the red-headed duck. It's also a duck. And just if we extended from mallard duck and made like a baby mallard duck, it would also be a mallard duck, and it would also be a duck. So pretty dope. So let's watch this in action here. We're going to loop over our new array of ducks. And this part will work a little bit differently depending on what language you're in, what actually goes on in this type of for loop here. But what we're going to see here is for let duck of duck array, we'll log our duck's age, and we'll see that each duck kind of ages a little differently, even though they all start at age 23. We will quack and we will swim, and we'll see that they do different quacks and swims. So you see our first duck here was just a plain old generic duck. So they get the plain age of 23, generic quacks out and paddles with their 2 little feet. Our next duck was the mallard. So you see they're 28 because they were 5 years older. They get the mallard duck's quack, and they still paddle with 2 little feet. And now when I get to my red-headed duck, well, he's going to be 22. He's going to be a red-headed duck's quack, and he's going to still paddle with 2 little feet because we never overrode the swimming. So here we go. Well, that's really cool. We're able to loop through our thing, and we can do the correct thing for our type of duck by looping over our now duck array. So cool. All right, so this is where we're going to really start getting into designing our good OOP design practice. This is just a little heading here. There's really no content to it. It's just kind of overlining what we're about to do over the next couple of iterations of our ducks, because we're going to keep making ducks until we make good ducks. All right. So first step is we're going to start talking about abstract classes. All right, what the heck is an abstract class, you may say? Oh my God, I don't know. I've never heard of this. I'm scared now. Don't worry, guys. Abstract classes are super simple. All right. So if we think about our classes of duck right now, we have duck and we have mallard duck and we have red-headed duck. What the hell is a duck? There's no such thing as a plain duck, right? So we have mallard ducks, we have red-headed ducks, we have duck decoys, we have rubber duckies, we have all other kinds of ducks, but we sure as heck don't just have a plain duck. So what we should do then, since it doesn't really make sense to just have a duck, is we're going to turn our duck into what's called an abstract class. So an abstract class is a class that cannot be initialized. So you can never have an instance of duck. But what it can do is define the implementations or just methods that you should be implementing in your children classes. Very often, abstract classes don't have any method implementations. They just have empty bodies saying, hey, anybody who's going to be a duck will need to be able to quack and swim. And that's how we're going to set this up here. But we could also give our methods an implementation that is going to be defaulted for all ducks if we really wanted to do that. It doesn't always make sense to do that, though. And in this case, quack and swim doesn't quite make that much sense to do that. All right. It might maybe for swim, if we say all ducks swim the same way, we could do that, and they always will swim the same way. You know, if they just, maybe you used to say they float, and then any type of duck could float. All right, so note though here, abstract methods do have a body, even if it's empty. So when I say a body, if you look here, I have defined quack and swim in my abstract. So note the abstract is the first word here. And we will come here and we'll have our empty body of these things. Don't do this. That's how we're working like an interface. But in abstract class, you do need the empty bodies if you're going to not implement anything. Cool. So here we just say, hey, if you're a duck, you have to have an age that's protected. And we have this get age that we're going to be returning back to them. So nothing too crazy. And then they have to be able to quack and swim. But we're not going to tell them how they quack and swim. We're just going to say all ducks need to be able to quack and swim. So if we look now, I can't initialize a duck class because it's abstract, and you cannot initialize abstract classes. Doesn't make sense. They're abstract, meaning, you know, they're a figment up there and there. They're an idea. So it's the idea of duck. So now we're going to make a concrete class. So what we usually will call these are concrete classes. And it's going to extend from duck. So now we'll make our mallard duck all over again. He's going to have a color and age. We'll still do our super age. And we're going to override our get age. And we're going to keep the same idea of adding 5. And now we're going to override our empty quack and swim abilities and make our own version here. So mallards quack and are swimming like a mallard. We'll do the same thing here for red-headed duck. Note it extends. Remember, extends is how we do this. We super age and all that fun stuff. We do the exact same thing, but now we have red-headed ducks quack and swimming like a red-headed duck. Cool. So now what we're going to do, once again, is we're going to make a new duck array. We can still make a duck array of abstract ducks because it's still a parent class. The polymorphism still exists. We just can't make an instance of a regular duck now. So now I have a list of my 2 ducks. We're going to loop over our ducks, and we'll see that they do their own, their own type of implementation. It looks like something went weird when I ran this last time. Let me rerun this. There we go. Now they're actually doing the right thing here. Swimming like a mallard and swimming like a red-headed duck. Okay, so we do see the right quack here. We do see the right type of swimming here because they both do have their own implementations of swim and quack. All right. So now my question is, what happens if I do this? What's going on with this color property? I say duck.color, and both my red-headed ducks have a color, and my mallard ducks have a color. Well, what the heck? I can't see the color, but if I did something like a mallard dot color, I can see that it's black, but if I do it like this, I don't. What is going on? So this is because we are now having an array of ducks. So we're going to be treating these things like they're ducks. So if you don't have that property or method defined in the parent class of duck, I won't be able to use it in a duck array. I know, this is where it gets a little tricky, right? This is where stuff gets tricky. So I'm going to log the duck.color, and we're going to see I can't do it because the duck type doesn't have color. So if I wanted that to work, we're going to come up here, and I had left this line commented out earlier. So we're going to come here and add in color string to our duck class. And now we can come back and we can run this, and we'll see, because now the color exists on our class duck, and it's public, so I can access it, and it was public here, so we can still access it from the child class. So we had to add it to our parent class so we could be able to access it using the duck super type. Interesting stuff, right? All right, I'm going to go ahead and comment that back out. All right. So now we're going to have to imagine we have to add the ability for our ducks to fly. This is going to be simple to add a new method to our abstract base class of duck and then implement its specific functionality in its children classes of red-headed duck and mallard duck. And for simplicity, I'm going to remove that color property since we don't need to talk about it anymore. So I still got the age, got the quack swim. Now I've added fly to my abstract class. And now we have our mallard duck, and we're going to institute fly like a mallard. This is all we really added here is fly. And in the red-headed duck, we added fly here. Cool. Nothing really crazy going on there. I didn't put any examples of doing this or using this because there's just not a lot going on there. All right. So that's fine. We have fly now. But now our boss comes to us and say, man, we have a new type of duck. A duck decoy. Okay. So now this is going to kind of pose a problem to our design that we have designed up here. So I'm going to build up my duck decoy class. Since ducks, it's still going to be able to quack. It doesn't know how to squeak. Oh, crap. It doesn't know how to quack. It doesn't have that. And then swim. Well, he floats. So he's going to say he floats on the pond like a decoy. And then, we're going to talk about flying. Well, what the heck do we do here? A decoy duck can't fly, right? This makes no sense. Maybe a decoy duck could make a squeaky noise or something. I don't know. But now we're really in a pickle. Because now we have the ability to fly on a decoy duck, but he really shouldn't be able to fly. Right? So what should we do? All right. Well, never fear. Interfaces are here. And they'll let us do this in a much cleaner, much better way. But before we get to that, I did put in a in-class exercise. And they need to create a class car, 2 subclasses of smart car and truck, and they all should be able to brake, drive, and honk. Smart car is going to make a hum sound and honk with a meep. Truck's vroom, honks with a bwamp. And then a truck or a smart car brakes with the sound of squeal. So either way, they're both going to squeal. So here, we're just kind of trying to design this system. That's kind of the point of we're trying to get them to do this. And so here, since they both share brake, we made brake be in our class car. And then we're going to have truck extend car, and we're going to have smart car extend car. And they're going to have their own implementations, and we're going to go ahead and do this. And maybe this should be an abstract class here. Would make a little more sense. So we can make that an abstract class. Easy enough to do that question. All right. So interfaces. Let's redefine our ducks now using interfaces. Interfaces are generally named with a suffix called able, because interface says something that implements it is able to do these actions. All right. So interfaces also work with polymorphism. So if you implement something, you're considered to be one of those things that it implements. So when we use an interface, when a class uses an interface, it implements the interface. So I guess I kind of skipped ahead to that. And we can implement many interfaces, yet we only extend one class. So interfaces are really important here. So the idea of interface is it can enforce many different methods or properties onto another class. And that's so we can make 50 classes that are all completely different, but if they interface with the same interface, we know they can all have the same ability. So even imagine we just have a whole just plethora of different classes that do all kinds of different things, but maybe all of them, just like in, maybe all of them have some way to print them as a string. And then they could all implement the toString interface. And then we know that anytime we have anything that implements the toString interface, that we can use our .toString method to get a string version of that. Kind of the idea here with interfaces. Interfaces and types are pretty similar. But, generally, interfaces are created. Say the class will work with anything that needs this interface. There is a more in-depth here on this link. Why types and interfaces are different. Feel free to go through that. So here, just a little example. So interfaces are created with a class. They will work with anything that needs an interface. So you can think of a CD as interface. There are tons of different CDs with information on them, with different information on them. But you can put any single one of them into a CD player, and you can play them. So the CD is an interface that works with the class of CD player, and then different artists can use the CD interface to create their own CDs filled with their own music, and no matter what, they'll all be able to be played on a CD player. Also to note, interfaces do not have method bodies. Remember, abstract classes have method bodies. They could be empty, but interfaces never can implement anything. They don't do implementation. They just describe what it needs to do. So now what we're going to do is think of a smarter way to arrange our classes that we built up here with our decoy duck, our red-headed duck, and our mallard duck. And what we're going to realize, because this is flying, but we don't want all of our ducks to be able to fly, is it's going to be a lot easier to make interfaces for them. So what we're going to do now is make our abstract class of duck, but now instead of being able to quack and swim, he can't do any of those things at all. He has an age, and that's all. And now we're going to make an interface, quackable, swimmable, and flyable. And that's going to say, hey, anything that's going to implement quackable has to have a method called quack. Anything that uses the interface swimmable has to have swim method. And anything that implements the method flyable has to have a method called fly. So now we could assign, quackable, swimmable, and flyable to mallard ducks and to our decoy ducks, or red-headed ducks. And that's what you see I do here. We say duck extends duck and then implements quackable, swimmable, and flyable. So we're getting our inheritance and our interfaces. And we can see here now our mallard duck can quack, swim, and fly. And our red-headed duck is going to be able to do the same things, quack, swim, and fly. And we have our own implementations for each one of those. But decoy ducks don't fly, so they don't implement flyable. They're just going to implement quackable and swimmable. And see, they are only going to have quack and swim. So now we're going to make our array, but this time we're going to say this is an array of quackable types. So now only things that can quack can go into this array. And what we'll see here is I need to run my cells if I want to actually run this. All right, so now you can see when I do my duck.quack, I get my different types of quacks. And note my decoy duck just says I don't know how to squeak. All right. But now, look, if I did this or try to do duck.fly, I couldn't do duck.fly, right? This goes back to the same problem we were seeing when we had the loop of ducks. Because only people that can fly are flyables, not quackables. So we got to make sure if we wanted to be able to fly, we can make an array of flyables, and then we could do .fly. But we can't do it here. If I made an array of flyables, I couldn't put a decoy duck in it because it's not flyable. Oh, and I did a whole example here. So here, you said I can put a mallard duck in here and a red-headed duck, and they can fly. But if I try to put a decoy duck in here, it won't work because it's not a flyable thing, so it can't even go in that array. And then here I made it still of ducks, and you can see this is how I could get the age out, but I could not fly or do any of those interfacing things. All right, so now they have in class exercise 2, they're going to make a class called music media. Or interface of music media that states anything that implements it should be able to play and create classes, CD, tape, and record that implement the playable interface. CDs when they to implement play, they're just going to say spins and reads with layer, magnetic tape is read, and needle in grooves. And you see here we've made our music media interface that says you can play, and we implement it here in each one of our classes. Pretty cool. And then you can see they all have their own way to play because they all interface with the same type of stuff. So this is the idea. Now, anytime I need something that can play, I know if it is a member of music media interface, I will have the ability to play. So I can make an array of CDs, tapes, and records, and I could play them all with my stereo or whatever it is you're trying to use to play them. Pretty cool. But, that was a pretty cool design we made up here, but it wasn't perfect. So we need to make it a little bit better. And because the problem is, we're going to find out is when our boss comes to us and say, hey, let's make a rubber ducky, now we got another problem. All right, so, that's another thing we got to deal with. What's a rubber ducky? Well, it does, it squeaks, it doesn't quack, and, it floats, it's just kind of a little bit different, right? And it definitely doesn't fly. So what we're going to say is we're going to assume now that a mallard and a red-headed duck both quack and fly and swim the same. And most ducks will have the same sort of flying, quacking, and swimming mechanism. We'll say decoy ducks still fly, quack, and swim differently. Now we are tasked to add our rubber ducky. A rubber ducky will not be able to fly like our decoy duck. Our decoy ducks can fly for some reason. All right. Did I really make him fly? I thought I said they couldn't fly. Yeah, so those decoy ducks can't fly. But maybe they can down here. It will also quack in its own squeaky way, and it will swim like a decoy duck does by floating. All right. We'll figure out what the heck I mean by that. So we have our interface quackable, interface swimmable, interface flyable. All right, those are all of our interfaces. Cool. Now, we're going to design this a lot differently. So now we're going to make a class of quacks that implements quackable, and it's going to give us the quack. We're going to make a class of squeak, and it's going to give us the squeak. Okay? We're going to give the class of muted, and that's going to just say the sound of silence. And so we have different ways we can quack now. We can have quacking with a quack, quacking with the squeak, or the sound of silence. Now we're going to find our different ways we can swim, and we're going to pull them out to their own classes. So if you float, this is going to be our implementation of swimming for floating. For swims, we're going to say they have a standard duck swim. And for flying, and then we're going to do flying, and we'll have fly with wings, and I don't fly. So we have our different ways to do flying. And this is going to make everything a lot nicer, because we were saying what a pain, this stuff up here was when we were trying to loop over our ducks that were flyable and our ducks that were quackable, but we didn't have access to everything. It was a real pain in the butt. So what we're going to do now is in our abstract class duck, it's now going to implement all of our interfaces of quackable, swimmable, and flyable, and we're going to give them these special attributes to hold their swimmable class, their quackable class, and their flyable class. And we're going to make some setters and getters for these, so I just made a bunch of setters here. I just made setters. I didn't bother with the getters, so we just made some setters so we can set our abilities. And we have our methods here. So now all of our ducks that extend ducks should be able to swim, quack, and fly. But they're going to use this their ability class .swim. So what's really cool about this is we're going to be able to change this stuff at runtime. This is dope. All right. So now our mallard duck extends duck, and we're going to set what all of its abilities are here. So we're going to say its swim ability is swims, because swims was our class. That says standard duck swim, right? So we're going to do that. We'll do quacks, and that's the regular old quacky sound, right? Quack. And we will give it fly with wings, because it can fly with wings. Red-headed duck, we said they were going to act the same. Okay, so rubber ducks and decoy ducks both fly the same by not being able to fly. So we're going to say never flies and never flies for their flyability. Rubber ducks can squeak, but duck decoys are muted. And then they both just float on the water. They don't actually swim like a duck. And now you can see, we can say let all ducks be an array of ducks, and I can put all my ducks in here now. And now when I loop over them, I get the right ability that I expected. And they all work. So my duck can fly, my duck can swim, and my duck can quack. And they all will be doing it in their correct way. Pretty cool. So this is kind of our God answer key for their homework. Their homework answer should look pretty much just like this with different words. Because their homework is to design a flexible OOP system just like this. About some other stuff, about some gamer pieces. So what's really cool here, right, is because now I could actually come here and I could change. I could say duck. I could make my instance of mallard duck, right? And then I could actually say get that mallard duck, and I could change out his swim ability and give him somebody else's swim ability. So we can make mutant ducks. And we can do it really easily. So this is so cool. Like, I hope you guys understand how powerful this is, what we're looking at here. Now we got this polymorphism section here. So once again, I can make all my ducks of type duck, and I can still do it like this. And now I can still call them in my thing. We can see all of them doing their thing. Pretty cool. So we can actually make these all ducks. And then we can just say let duck of ducks. And then it's automatically going to be a duck array. We don't even have to declare it if we don't want to as a duck array. And this is what I was talking about with changing the implementation. So now rubber ducky, well, maybe my rubber ducky, I want to make him be able to fly. I can say, hey, you're going to fly with wings for your fly ability, and now he can fly with wings. Pretty dope. All right. So the whole idea that you really want to be driving home here is the idea of what we're doing here, which is programming to interface. And that's not really a great word because, as you can tell, we have interfaces, but we also have, types and super types and all kinds of stuff going on here. So the ideas really should be better stated as program to super type. So the declared variable should be a super type, should usually an abstract class or an interface, so the objects assigned to those variables can be of any concrete implementation of the super type, which means declaring the class doesn't have to know about the object's types. So it is really cool idea. This is why we have pulled all this out. This is why we now have our abilities inside of the abstract class that we can swap out, because we are trying to program to interface. All right, and then we have this part about extending interfaces. An interface can also be used a lot like a type. The main difference here is an interface describes the object, while a type defines the object. All right, so here you're seeing my interface is human. I'm going to have a type of post. I'm going to make an interface called poster, which is going to extend human. And it's going to have a property that's post, which is a post array. That's why we have this here. And our last post, which is going to be a date. Then I'm going to say let my user of type poster equal Joe Biden, and that's a zip code. His last post is going to be a date, so I had to make it a new date. And then he has his posts here. And note, we have to implement all the things that are in human and in post. Or sorry, and in poster. Because it's first name, last name, zip, post, and last name. Awesome. We're going to go take a break. We'll come back to generics.